The last part here with forthright dragons tells us a farmer comes across two dragons that are in a heated discussion. He asks each about their color and type, and Dragon A says something a little bit different than we had in some of the past statements. He says, if I am rational, then I am red. Dragon B says, I am a red predator. Dragon A is also a predator. Okay, so let's talk a little bit about if-thens. If-thens are oftentimes referred to as implications. So an if-then is synonymous with the statement implication. And implication just means that from one thing, another thing follows. And that statement can often be written like this. And I'm going to use P and Q for a second. No, in fact, I'm going to use not P and Q. I'm going to use S and P. Okay, and the reason I'm going to use these, I'll clarify in a second. So here's the if. So if S occurs, then that means that implies that P will occur. Okay, so this, to give a little bit more insight here, this is called the sufficient statement. This is sufficient for this to happen. So if this happens, this thing is necessary. So oftentimes you'll hear it is sufficient and necessary, and that often refers to an if-then statement. So how does this look? Well, let's look at a truth table to make this make a little bit more sense. The reason I picked S and P is because I'm going to have S stand for it is sunny. It is sunny outside. Okay, so it is sunny outside, and P is going to represent you can go to the pool. Go to the pool. And my intent here is to have you think about a parent saying this. So if it is sunny outside, then you can go to the pool. Well, let's suppose that it is sunny outside and you get to go to the pool. So these are both true statements. Well, what does that say about the implication? Well, that means that the implication is true, because essentially if you think about it from the standpoint of the truthfulness of your parent's statement, they said that if it's sunny outside, which that did happen, then you can go to the pool, which that did happen. Since the sufficient led to the necessary, your parents were telling the truth, so that implication right there is true. Well, what happens if the sufficient part happens, if it is sunny, but your parents say, no, sorry, you can't go to the pool today, then were they being truthful, or were they being, I'll just say it outright, were they lying? Well, they were lying, right? Because they did not hold to their word, so the outcome of that implication is false. They gave a false implication. Okay, well, this is where it gets a little bit more interesting. What if the sufficient doesn't happen, but you do get to go to the pool? What does that say about the implication? You might say that it's false, but it's actually true. And the way I like to think about this is your parents they didn't lie to you. They just said, if it is sunny, if this happens, then you definitely get to go do this. They didn't tell you what will happen if it isn't sunny outside. They just said, if sunny happens, then you get to go to the pool. In this case, it just so happened that, if it's sunny outside, you get to go to the pool, but it wasn't sunny, and they're like, yeah, go to the pool anyway. Well, they were still truthful. They still met the demands of a if-then statement. So even if it's false, so if it isn't sunny, but you don't get to go to the pool, they were still being honest. The only time when the implication is false is if the if happens, but the then doesn't. So for programmers, think about it, that if x equals 2, then take x equals x plus 1. So basically, if the variable that's in part of the program has a value of 2, then add 1 to that value. Well, what your computer does is it says, okay, let me check, is x equal to 2? Okay, it is, so I'm going to proceed on to the then part. And that doesn't really hold for the other cases, but that just kind of emphasizes that if is the sufficient demand. That's all that has to happen. That's purely sufficient for the conclusion to take place. Oh, and oftentimes the sufficient is called the premise, and the necessary is called the conclusion. So that's oftentimes how we write things. Okay, so let's jump back to this. So here we have, if I am rational, then I am red. Okay, what does that say about Dragon A? So Dragon A says, if I am rational, then I am red. Dragon B says, I am a red predator. So I am red and I am a predator. He also says, so in other words, I can say, and Dragon A is also a predator. So A is a predator. Okay, well, wait a minute. It's probably easier to start with Dragon B because you probably noticed the contradiction already. He calls himself a red predator. Well, number one, a predator will never be honest about saying that he's a predator. And if he doesn't say that he's a predator, what does that tell us? Sorry, I'm trying to jump screens here. Well, that means that this is a false statement. He can't be a red predator. Okay, well, what other options are there? If it's not possible for someone to be a red and a predator, then the only other things that he can be, so I am not a red predator, well, that means that logically he could be a red rational, he could be a gray rational, or he could be a gray predator. Okay, so this is where we now have to ask ourselves, what does this game allow us to conclude? Well, because we know that a predator always lies, and a predator would never tell the truth, but a rational would never call himself a predator. Therefore, we know that this dragon cannot be irrational, and the only possibility left would be that he's a gray predator. So, in fact, this must be true. We don't even have to debate this and try other things. We know that he's a gray predator. And again, we know this because he can't be irrational. Rational would never call himself a predator because that would be a lie. Okay, so we now know that Dragon A is that he is a red predator. But then he says that Dragon A is also a predator. Well, since we know that Dragon B is a predator, we know that this statement must be false. That A cannot be a predator because then he would be honest about A, and we already know that Dragon B is not an honest dragon. So we are able to conclude that Dragon A must be rational. And I probably shouldn't use the arrow. I'm not trying to say if-then here. This is where you have to be careful with the arrow after you're introduced to that. A must be rational. Alright. Okay, so what does this statement say? This statement says, if I am rational, then I am red. So if I look at rational, and I look at red, and then I look at red, if I am red, then I am rational, when is the statement true? If he's red, and he's rational, then the if-then part is true. If he's red, but he's not rational, then the statement is false. And false, true, false, false, true, true, and false, false, true. Okay, so he would be telling the truth if he said, if I am rational, then I am red, but suppose he's not rational, and he's red, well, that implication is still okay because he wasn't lying. He just said, if I fall under the rational category, then I promise you I am red. Well, he is rational, right? This is a true statement, and it says, if he is rational, then he is red. Well, a rational tells the truth, and therefore we know for a fact that Dragon A must be a red rational. So we've concluded that B is a gray predator, A is a red rational, and we're good to go. So that's one of the main importances or important components of of dealing with an implication. I want to do just one more thing real briefly. We also talked about this little statement, which kind of looks like a backwards, sideways L, and this is also applied to statements to mean that statement is not true. So, not P. This symbol stands for the word not, and is often referred to as a negation. It negates it. It basically, think about positive, negative numbers. If you negate positive 6, you get negative 6. It's essentially becomes the opposite. It doesn't, whatever P implies is not the case. Now you've got to be really careful with these because it's really easy to say, to make big claims. For example, my name is Milos, and I have, let's see, I have a table saw. Okay, so I have a table saw. All right. Well, let's suppose that this statement, and I probably shouldn't use capital letters. I'll use lowercase here. I am Milos and I have a table saw. Well, what if this statement is false? Okay. Well, we kind of already did this before. If this statement is false, then that means that it's not true that I have that my name is Milos and I have a table saw. A common mistake is to say that this means, well, you're not Milos and you don't have a table saw. But in fact, these two things are not equivalent. So this is not necessarily the conclusion that we can draw, that my name is not Milos and that I don't have a table saw. Now, in reality, if this statement is not true, then that means I'm not Milos and I have a table saw. That could mean that I am not Milos and I don't have a table saw, or it could mean my name is Milos and I don't have a table saw. So I essentially am saying that one of these three is true. Okay, well, let's do a real quick truth table for this and see if we can come up with any simpler way of expressing a negation. So here's MT, and I like to do my true, 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 false, false, true, false, false. And now I will do M and T, because the negation is just the opposite. So if M and T are both true, then the and is true, and it's false everywhere else. Okay, but if I negate that, then I get basically the opposite of M and T, right? Because negate means the opposite of, and the opposite of true is false. And similarly here, we would get false, true, true. All right, well, wait a minute. This right here, doesn't this look a lot like the values of a truth table we've seen before? Well, to me, this says, okay, well, wait a minute. If these three are all true, this is the same thing as, so I'm going to write M, not M and T. It would give me the same truth table as not M or not T. Okay, well, wait a minute. Let's see how this pans out real quick. If I know that M and T are both true, then that means not M and not T would both be false. And that means that the result of that if M and T are both true and not M and not T are both false, then not M and T would be false. So all I'm doing is I'm essentially, imagine that I inserted these two columns in here, and I'm keeping track of the conclusion. So not M and not T are both false, then I get a false out. If one is false but the other is true, that's my second row. If not M is false, which is really saying that M is true, and T is false, that means not T is the opposite, it's true. Well, that gives me the conclusion of true. You can probably see where we're going with this. True, false gives us a true, and true, true gives us a true. Okay, well, wait a minute. If either not M is true or not T is true, anywhere where either not M is true, which is here or here, and anywhere where not T is true, which is here and here, the outcome is always true. So that means if not M is true or not T is true, then I'm equal to the same truth table that I would get if M and T was basically not true. If I can say not M and T, then that's the same thing as saying either M is, I shouldn't say either, M is not true or T is not true, or possibly both. So hopefully that helps a little bit. I know it gets a little confusing at first. We'll work a lot more on this, but I wanted to sort of give you a little bit more of an introduction so that when we come in on Wednesday, we have a little bit more power with which to work. So I'll see you guys then. Have a great weekend.